Hi everyone, and welcome back to this video series in which we explore the Python package Turbulucid. And this episode we're going to cover two things. One is getting your data into Turbulucid, and then we're going to do some basic plotting to get sort of the first feeling for how actually working with the Python package works. Okay, so as you can see, I again have ParaView fired up here. And the reason for that is that I think for most of the users, the routine is going to be more or less the following. You start out with some kind of 3D dataset, which you look at in ParaView. And then you extract some sort of two-dimensional data one way or another. For example, here I extracted this slice. And let's say that this is the 2D data that I want to look at in Turbulucid. Now what I can do is select the slice here in the pipeline browser. And then I can go to File and Save Data. Okay. And in the files of type, I can choose VTK multi-block files, .vdm. So I think it might vary a bit what type of VTK format you will get depending on what your original data set is. So in my case, this is an open foam simulation. But I'm pretty sure you should be able to save to either a VTP or maybe a VTU, something like that. So let's choose that. And now let me just navigate to Jupyter. There we go. And let's call it demo. All right. Don't really need to change anything here. Let's press OK. And now we can actually test if this works. So now we can click on Open and try to open this VTM. Voila. So now we have the slice as a separate file. Now, if you're not familiar with what a .vdm is, that's a multi-block dataset, which means that the .vdm file itself is just a XML file which tells ParaView the location of other files which actually constitute the separate blocks. And those are typically VDP. So if you look at the directory, you have this demo.vdm, and then there's a directory called demo, which was also created when we saved the data. So if we go inside there, we actually see that we have this demo00.vtp. So that's actually the data is actually this. And in this case, we only have one block in the multi-block data set. So it's actually redundant to have the VTM. So what one can do is just copy the VTP out of this demo folder and use that. And that is what we're going to do. So VTP is one of the formats Turbulucid can read in. So that's VTK polydata. The second format is .vtk, which is basically the same thing but legacy. Or actually, I think it's a bit more general. So the .vtk, you can have different types of VTK data in a VTK. So it can be unstructured grid or polydata or structured. I think at that point, everything was lumped into one file format and then they split into different ones. So .vtk and .vdp, I'm not going to talk about what to do with other file formats. There's also a native format for Turbulucid, which I'm not going to talk about too either, because I think this routine is what's going to fit most of the users, honestly. So this is more or less the first part of the video then. Now let's finally get to some more fun things, and that is doing some plotting. So I'm just going to go ahead to this document. Let me see. Jupyter. There it is. So I'm going to delete the VTM file. And I'm going to copy the VTP file here. There we go. and we can remove this. So now we have a .vdp file which we can work with. So I've chosen to use a Jupyter notebook for the demonstration. So I have a Jupyter notebook fired up here somewhere. There it is. I think it's a nice environment to make tutorials, but of course this would work from whatever Python console you choose to use. I haven't done much here, so I only imported Turbulucid and then matplotlib and NumPy. So this is sort of a fresh start. Now, before we dive in, I want to briefly go to the Turbulucid GitHub and show you around a bit, because one thing is that if you're not really into watching videos and would like to just sort of dive in directly yourself, what you can do is use a tutorial which we have. So here it is under dive in the README. There's a link to the tutorial, and that's also an IPython notebook, so it'll actually render on GitHub. So as you can see, here we go through some different types of plots and things like that. So if you are more interested in just grabbing something to work with directly, that's probably the best thing to do. Now, the second thing I wanted to show you here is that here on the top, there's a link to GitHub Pages, which is a website associated with a repository. And if we click on that, it will provide you with some documentation. So there aren't any sort of text instructions here. That's only in the README. But this contains the doc strings for all the classes and functions which are in the package. So for example, we can go to plotting, which is a submodule or sub-package. And here we can see that there's quite nicely written doc strings for all the functions, explaining all the parameters, what they mean and what they do, and what the functions do. So this is a nice way to explore what is in the package, and also, just to get a bit of help. Now, since these are doc strings, of course, you can also get this from your Python environment directly, so you don't actually have to go to the website. But this gives a nice overview, I think, of what is there. Okay. So moving on to finally working with some data. So to open a dataset, we have to create a case object. So it's capital C, case, and this will basically encapsulate your dataset. So the argument here is the path. So it should just be demo.vtp, right? Yeah, because we see it right here. Let's try to see if this works. It worked. Amazing. So now this little variable contains our data set. Now there's quite a bit one can do with the case. So if you're interested to learn, I would go to here, the case class, and it describes all the things you can do, like manipulate the geometry, like translate it, rotate it, things like that. Is an example. So one thing we're going to do is write case, or actually print case fields. And what case fields does, it basically gives us a list of all the data which we have in the data set. Okay. And yeah, one thing I should note is that the data is cell-centered. Okay, so it's cell-centered VTK data. If you have point data, it will actually interpolate it to cell data. So the reason I chose cell data is because OpenFOAM is a cell-centered finite volume code, and I mainly work with OpenFOAM, but also StarCCM and Fluent are also cell-centered, as I know. So that's the best way to represent exactly what you have in the simulation. So that is that. Good. So perhaps the most important plot function that we have in Turbulucid is called plot field. There we have it. And pretty much all the functions which are in Turbulucid, they accept a case object as the first parameter. So first we need to pass the case. And for the second parameter, we can basically choose any of these fields as long as it's a scalar. So one scalar is alpha water. So let's just choose that. So we can write alpha water. And let's just go ahead and run this. So there you go. That's pretty nice, but the figure is a bit small. So let's just add, let's explicitly construct a figure, fixed size. 18.6 for instance. There, much better. So yeah, you'll see what it is. So this is pretty much the same thing as if we have opened it here. It's the same data, right? Different color map, obviously. And now that we have this, we can start customizing. So, and you can use all the familiar stuff from matplotlib. So BLT, let's say X label, and let's call it X. Yeah, you see it pops up here. So because if we assign this plot field function to a variable, let's do that. Let's check what the type of that is. So as you can see, it's a matplotlib collections poly collection. So basically, you can do whatever you want to this plot as what you could do to a matplotlib poly collection. So essentially, you can just go to matplotlib's documentation, look up poly collection, and see what your possibilities are. And this is how most, if not all, of the Turbulucid functions work. So they do some VTK stuff under the hood and then glue it to some kind of matplotlib type. And that then gives you the possibility to interact using matplotlib functions. So it's more or less glue code. So what else can we do? Let's explore a bit more what the plot field function has to offer. So as I mentioned, you need a scalar field in order to make a plot like that. That's quite obvious. But what if I want, for example, to plot the streamwise velocity component, which is in the x direction here. Now I cannot put u here, or u mean, because if I do that, it will complain. The selected field appears to not be a scalar, and it's not, because u mean has 3 components, right? But it is completely okay to actually provide an array here instead. So we can in fact provide any array of the same size as your dataset, and then it will basically plot that as a field. So to that end, we can use 2 things. So one is we can actually see where the data is located for our case by looking at case.cellCenters. So as one might expect, cell centers will return the locations of the cell centers as a 2D NumPy array. So that sometimes can be nice. Now, another important thing is that we can return the values of each field by using the case object as a dictionary. So that means if I write case umean, I will get the values of umean. So if I want to plot the x component, what I can do here is, instead of writing just umean, I can extract the umean array and then grab the X component, which is basically just the first column. So now this is going to be a scalar, right? And of the right size, obviously. There we go. So this is the velocity. Let's continue looking at the plot field function. So we can, maybe we can try to grab the doc string. I always forget, is it help or... Right. There you go. Excuse me. Yeah, I always forget, is it help or is it question mark? I think help is in MATLAB and Python is question mark. There you go. So here you get the same doc string as you would get by looking at plotting and then finding plot field here. So this is just more nicely rendered, but as I said, you can of course get it from your Python environment directly. So let's see what type of parameters we have here. So case is your case object, field we have already covered. It's either a string, which refers to a scalar field inside case, or just an array. So then there are two parameters called scale x and scale y. Now, these allow you to scale the x and y axis, which is quite a common procedure. You want to, for example, non-dimensionalize them by some characteristic length. So observe it now, the x is from 0 to 2. Now, if I write scale x is equal to, well, let's just say 2, it will divide the x values by this factor. So divide, not multiply, okay? That's quite important. Yeah, as you can see, now it's from 0 to 1. Scale y works exactly the same. So no need to show that. Now there's also an x lim and y lim. So that will basically work just as PLT x lim and PLT y lim. That is, it will only render the data which is within the given box. So if I say the scale by 2, and then I say x lim, let's say from 0 to 0.5. Then we get this. And this is something to keep in mind, that this applies to the raw data, so not to the scale data. So it makes more sense, I suppose, to put this afterwards. A little bit less confusing, perhaps, because as you can see, now we are actually getting the values from 0 to 0.25 and not to 0.5, because this selects based on the unscaled data. Now, why would one need to do this instead of just writing PLT xlim afterwards? Well, the difference is that if you use the xlim in the plot field, it actually doesn't produce the polygons corresponding to anything outside this range, meaning that the plotting runs faster. And this is necessary because when datasets become large, like several hundreds, thousands of cells, plot fields becomes a bit slow. Because what plot field does is that it goes for each cell, and then for each cell, it creates a polygon based on the points forming the cell, which basically then constitutes one cell. And then it does it for each cell, right? So you get, if you have 100,000 cells, what it does is it produces 100,000 polygons. This is nice because the polygon is arbitrary, so you're not limited to any shape of the polygon. But the problem is that it starts to take time if there are a lot of cells. So this is sort of a way to avoid things getting slow, which can be quite nice. Let's go to the next thing, which is plot boundaries. So let me just quickly remove these. As we can see, by default, plot boundaries is set to true. And that is this black border here around the data, which shows the boundaries of the case. Now if I remove that, plot boundaries, false. Then, as you can see, this black thingy disappears. Finally, the last keyword argument is color bar, and that's whether to have or not have a color bar. So color bar false. Yeah, as you can see, it disappeared. So one reason besides for not wanting to have a color bar at all is to use color bar equals to false in order to have more control over the color bar. So if you create the color bar with the plot field, it's difficult to change its properties. For instance, its width and things like that. So there's actually a separate function which is called plt add color bar. Oh, sorry, not plt, tbl, of course. Turbulucid. There we go. And we need to pass the object which we return from the plot field, if I remember correctly. Yeah, and then you have the color bar back. So the difference is that you can assign this to some kind of object as well. Let's call it C, and then you can manipulate C to change the properties of a color bar. So this is a more flexible approach. Okay, so this is pretty much all there is to say about the arguments to the plot field function. I think it's quite obvious what it does. Now, an important thing which one should cover is that we see here this double star quarks as the last thing. And this allows you to pass keyword arguments into the patch collection constructor. So recall that we've established that the object returned by plot field is a patch collection. So obviously a patch collection constructor is being run within the function, and it accepts different types of keyword arguments itself, which you can look up in the patch collection documentation. For example, it's possible to pass an argument which would make the edges of each cell visible, which maybe can be good for some reason if you want to look at the structure of your grid. And generally this holds for other Turbulucid function as well. So usually there is this quarks in the end, which serves as a way to pass something extra to the constructor of whatever matplotlib object is being used by the function. Okay, so maybe let's cover just one more function, and this will be enough for this video. And that's a very simple function, and it's called plot boundaries. And as you might expect, it does exactly as what would happen if you have plot boundaries through here. So it will draw the boundaries, the outline of your case. So as usual, we pass the case object. And yeah, let's make the figure larger as well. Oop. There you go. So now you have an outline of your case. So this might be nice if you want to, for example, create a figure which describes the case setup. So, you can easily add arrows and text with associated matplotlib functions. So you can, for example, point to this boundary and say this is the inlet, stuff like that. So it can be quite useful. Now, it also accepts some parameters. Let's look at those. Not much. So just scale X and scale Y. And that you're already familiar with. And actually, I think scale X and scale Y go into most of the Turbulucid functions. So then you can also pass the quarks, in this case, to have a line collection, because this is just a collection of lines. It basically goes through for all the boundary edges in the VTK data and creates an associated line, and then groups them into a line collection. So some things you can definitely manipulate, for example, is the color of the line, right? It's probably either color or colors, and that will just be passed into the line collection constructor. Let's try color first. Let's make it red maybe. Yeah. So that's the power of this quark. So I don't have to create my own color argument here. Instead, I can just use the fact that already the line collection itself actually enables a lot of customization, right? So we can have color, we can have transparency, and all of those type of things. Okay, I think this is enough for this video. So we've covered how to extract data, and we've also covered some basic plotting, some basic properties of plot field function, and also the plot boundaries. I think in the next video we're going to continue exploring other plot functions. There aren't really that many, but I think they cover all the basic needs. So I think we're definitely going to look at how to plot vector fields, and maybe even streamlines, although I very rarely use that, but it's a bit cool to be able to do that anyway. So thank you for watching, and stay tuned for the next episode. See you then.